Welcome back, AP Calculus AB. This video marks the end of our adventure in Topic 6, and actually for me it marks the end of all my Calculus AB videos because I've already recorded all of Topic 7 since last year was the pandemic and I got to do those ahead of time. So I know you're very sad, but don't worry, you still have more videos ahead of you for review and Topic 7 because we haven't gotten there yet. But yeah, let's finish off Topic 6. This builds directly off of day 87, where day 87 was all about solving separable differential equations. And so if you haven't watched that one or you don't feel confident, you really need to be good with that before you do this lesson. Because this lesson is more solving differential equations, but we have a couple new elements that will be introduced. So let's go back to Algebra 1 for your opener, please, and go ahead and solve the two problems that are up there without a calculator, if at all possible. All right, hopefully you solved. You remembered to introduce a square root, very exciting, and I guess I can show some work, right? Whenever you introduce a square root, you need the plus minus that's in here, and so we end up with x equals -1 plus minus the square root of 3, which gives us two solutions. 3 minus 1 is 2, and -3 minus 1 is -4, right? Same thing over here. We add 5, that's 16. Okay, and then 16 divided by 2 is 8. We introduce a square root to the 8. I don't know why that became a plus. So we get plus minus the square root of 8. If you're feeling very bold, you reduce the square root of 8 into 2 roots of 2. And this is as far as we have to go here because there's no way to clean it up. Either way, 2 answers. Now, what we're going to focus on today are different ways to view equations. And in particular, if we are able to use part of an equation to meet an initial condition. For example, if we think about the equation y equals plus minus the square root of x, you should actually realize that that's not one equation. Rather, it's just, I'll call it a lazy, but maybe it's efficient or a shorthand way to write two equations simultaneously. It's showing us both the equation y equals the square root of x and y equals the negative square root of x. Right? So this is two equations merged into one. You'll find that graphing calculators, or Desmos or anything, will not let you graph that as a single equation because it's not a single equation. It's two completely separate equations. Now, you will notice if you square both sides here, right, if you square both sides, then that will give you y squared equals x, and y squared equals x is a single equation. In fact, it's the equation that looks like this. I have it up on the board. It's a sideways parabola, right? It's a parabola that starts at 0, 0 and wraps around the x-axis instead of the y. It's not a function. It doesn't pass the vertical line test, but it is a parabola, just a sideways opening one. Now, if they asked you to solve this equation, or rather put it in the form of y equals f of x, that of course means you should isolate y. So, right, if we had y squared equals x, we would isolate y by introducing a square root on both sides. Okay, we have learned though that when we introduce a square root, we need to include a plus minus, and it gives us this. This, though, is not in the form of y equals f of x. Rather, you could maybe argue that this is in the form of y equals f of x and y equals g of x, because there are two functions here, the positive square root of x and the negative square root of x. So if you're asked to solve in the form of y equals f of x, they mean list the single equation. Now that's kind of tough because if we look at these two equations here, they both together, or they both separately, do not make the same graph as the original equation. And I'll show you that on the computer right now, right? If you take each of these to be separate, I'm going to type these out down below. If we have y equals the square root of x, that's only half of our parabola. And putting the second one in, y equals the negative square root of x, gives us the other half of the parabola, though we should probably see this in green. There we go. And so when we put those two together, they make the red graph, but we need both of them. However, if you are asked to solve for y equals f of x such that f of 9 equals negative 3, then we do have the ability to write only one equation. F of 9 equals negative 3. I think that's the point, 9 comma negative 3, right? If I turn off this red one, we look at the black one and the green one. Which graph contains that point? Oh, only the green one that's down here. So if you were asked to solve this for a single equation that meets up or that contains the point f of 9 equals negative 3, then you would be expected to write the final equation, I'll do it in green, y equals the negative square root of x. If you wrote this guy up here, you would be incorrect because you would be answering with two different equations, one of which does not contain that point. Right? That would be if they asked you to solve for some x value and you're like, I think x is 5, but also maybe x is 3. Well, which one is it if I just want a specific x? You have to list the correct one. You can't just list lots of answers and hope that the correct one is in there. Why is this relevant? Well, we are going to go ahead and take a look at a differential equation that may have multiple equations as an answer. We actually saw this when we checked solutions to differential equations, and we saw a single differential equation can have many different equations that work when you check that solution. So let's warm up. Find the particular solution y equals f of x to this differential equation that meets this initial condition. Okay, cool. This is just like what you did last class. So let's go ahead and see what you can do. I'm going to do the same that I've done in the past, divide my paper into 3 sections. I've just found that's generally the easiest. And let's have you work through it. It's a separable differential equation. Feel free to unpause once you're done. All right, moving a little more quickly this time. We're going to multiply both sides by y, so I get y dy, and then multiply both sides by dx, x plus 1 dx. This is actually a very nice looking differential equation. I think when we integrate each side, we're going to be pretty smooth flying here. 1/2 y squared equals, let's see, antiderivative of x is 1/2 x squared, and antiderivative of 1 is x, and don't forget your plus c. Great. Easy enough so far. Then initial condition. Our initial condition is the point 0 comma negative 2. So we take this guy 1/2. We need to work in that initial condition. And don't forget, you don't need to show all of this work. You do need to show that you found the value of c somewhere, but you can show less than this. Just never a bad thing to show more if we're on a video. 4, half of 4 is 2, and we get c. Nice. All right, on to the last part. Crushing it so far. So our last part, we have 1/2 y squared equals 1/2 x squared plus x plus 2. We need to isolate y. I'd get rid of the 1/2, probably multiply everything by 2. That's going to give us 2x plus 4, and then take the square root. Don't forget, when you introduce the square root, you need the plus minus. Or do you? Because if you leave your answer like this on the AP exam, you will not get the final point because you did not meet their requirements. Their requirement said find a particular solution y equals a single function of x, and you gave them 2 solutions. You gave them both a positive square root graph and a negative square root graph, and you need to choose which one. How do we know which one to choose? Well, it's all about the initial condition. The question becomes, and I'm just going to cheat and just write a positive one versus a negative one here, which one of these equations contains the initial condition? Right? And this is kind of tough because if they had let you keep your equation not in the term of y equals something, you could have stopped here. This equation contains the initial condition. We know that because we plugged in the initial condition to find c. But when you isolate y, things get messy. So what do you think? This initial condition right here, which equation will contain that? And hopefully you're saying, well, if this square root only gives us positive answers, but this one gives us negatives, and this is saying when you input 0, you get a negative answer, then I think it has to be this second guy. And you'd be correct. So if you wrote 2 of them, cross out 1 of them. We don't want that on your paper. If you cross something out, the AP readers have to ignore it. And we would just finish with our final equation right here. You have to choose the correct branch of the answer. Now, what does that actually look like? What are we doing here? Well, what I took some time to do is to create a slope field for this differential equation. I didn't want you guys to do it. I made one though. So here is my slope field. Okay. If you look at this slope field and you think about how many graphs are there, well, how many graphs do you see? Because I see a whole bunch of them, right? Maybe you'll see that depending on where your initial condition is, the graph of the solution is actually going to run into these kind of asymptotes right here. Okay, and you might not be able to see that they're asymptotes right away. And honestly, it's very tricky to see that these are asymptotes sometimes. Sometimes this could just be a diagonal line, right? But the reason I'm pretty convinced they're asymptotes is I actually graphed the solution we found over here, that negative square root. It's right here. Okay, and when we graph it, notice that it does go through our initial condition, 0, -2. That's right on the y-axis, right? And because it went through there and we run into these diagonal asymptotes, we can't pass them, and so we're stuck in that kind of lower region, right? We could have done that here. Here's 0, -2. And then if you follow the points around, you get closer to the asymptotes, but you don't cross them. Well, what would happen if we had a different initial condition, right? What if instead of 0, -2, we had the point 0, +2 up here? Can you picture that? Well, I actually created that one too. And if you have the point 0, 2, look at how your graph changes, right? You would even know the equation for this one, right? This would just be your square root of x squared plus 2x plus 2, right? Plus 4, I guess it was, huh? So that's the same equation, but the positive version. So you can see that we wouldn't include both equations. It's 2 completely different graphs. And the equation that you include depends on the initial condition. Just for fun, any idea how you'd get your graph to open to the left or to the right? Because it actually turns out if you use an initial condition over here and you solve for y again, it doesn't quite work out. Things get a little hairy. But I think I maybe gave it away. But yeah, if you have an initial condition somewhere else, isolate x instead of y. So if you have 1, 1 and you isolate x, that will cause your graph to open to the right. Or, well, I didn't do the other one, but -1, 1 would cause your graph to open to the left. So don't forget that these differential equations can have multiple solutions. And if you find multiple solutions like a plus minus, you are required to choose the correct branch there that matches or contains your initial condition. All right. So, just like we did before, there are some review questions on here, like A and B that are combined together, and then there's some new stuff, C1 and C2. So I'm going to let you guys do A and B, and then we're going to work together and do C1 and C2. However, you should already know how to do all of these. There's nothing really new. So when you are ready, try C1, try C2, and then unpause me and I will go through those. If you want to see the answers to A and B, they're posted on Teams. Ready, set, go. All right, let's take a peek at C1. We want the particular solution in the form of y equals f of x, and so I'll do my normal, split into 3 pieces here. They're called C1 and C2 because I adapted these problems a bit, by the way. There wouldn't be a C1, C2 on the AP exam, though they have done like subparts before, but not in a long time. So here we go. Split the variable first. 1 divided by y cubed dy is equal to x times dx. We're going to take the antiderivative of each of these, but I took a quick second to rewrite my y's. We add 1 to the power, which means we need a -1/2 out front, and that's going to be equal to 1/2 x squared plus c. I'll probably take a quick second to rewrite this. I think it might be a little easier if we treat this as -1/2 times 1 over y squared. equals 1/2 x squared plus c. We'll have to do it eventually, so might as well do it now. And now let's look at the other side. Initial condition, 1, 2. All right, so that means our y is 2 and our x is 1. There we go. Cleaning this up a little bit, I'm saying negative 1/8 equals 1/2 plus c. We have to subtract 1/2. Don't forget 1/2 times 4 over 4 is 4 over 8. And so I'm saying c is negative 5/8. Okay, let's work back to our equation. Negative 1/2 times 1 over y squared is 1/2 x squared minus 5/8. I will get rid of this negative 1/2 first. Let's multiply everything by negative 2. That's going to give us negative 1. I'm deciding, I'm going to keep this as 2 over 2 x squared minus, and the 2 is going to cancel the 8, so make it negative 5/4, but positive. There we go. And the reason I did that is I want to add these two together to make them into a single fraction to make this easier to flip. We covered that last class. So 2 over 2 is actually the same as 4 over 4, right? So I have negative 4 x squareds plus 5 over the common denominator of 4. Flip each of our fractions. Y squared is equal to 4 divided by negative 4x squared plus 5. And then introduce our square root. Y equals plus minus the square root of 4 divided by negative 4x squared plus 5. But wait, we're not done. We cannot keep both a plus minus. We need to choose the right branch that matches our initial condition. How do we know? Just substitute in the initial condition. We need to substitute in 1 for the x's and get an answer of positive 2. Well, this is pretty easy. Which answer will give us a positive branch? Oh, right, the positive square root. Do you need to put the positive out front? No. You would probably just write it there. If you put the positive, are you wrong? No. We just assume that if there's nothing, it is just the positive branch. But wait, find the particular solution with the initial condition 1, negative 2. Oh, well, the nice part is we can skip all of this. We already did this, so let's get right to the initial condition. Right? So my initial condition is 1, negative 2. So I have this negative 1/2. I'm doing the initial condition. I'll probably work sideways this time because I don't have as much room. Times 1 over negative 2 squared equals, and then this was 1/2 times 1 squared plus c, right? I'm starting right at the top section because when we do the separable differential equation, we still get the same equation. Nothing's changed there. Things will start to change with this initial condition. Looking at this though, I'm seeing negative 1/8 equals 1/2 plus c. Isn't that exactly what we saw here? So I think c is again going to be negative 5/8. I got the same c value with that initial condition. Will that always be the case? No. I very carefully picked it so you did get the same c value, so you had to do a little less work. You could have gotten something else. Okay, well, where are we now? Well, now I think we should probably move into this last realm over here. But wait, if c is the same value, don't we know that that's the answer now, right? See, it'll be the exact same equation. So when we isolate y is going to be that same square root, 4 divided by negative 4x squared plus 5. Or is it? Because I need to make sure if I substitute 1 in for x, I get an answer of negative 2. And this square root only gives positive answers. So don't forget that this was originally a plus minus. We need to choose the other branch of the square root, just making sure your solution fits the initial condition. Now, hopefully we're feeling okay on that because now we're going to go back to algebra again and look at another case when this can happen. Sometimes we have absolute value, and some of you might have done a really nice job of learning absolute value, but I found that many of you forget a few things about absolute value. Now I'm just going to focus on linear absolute value equations, and I always make my freshmen say linear absolute value because they always think, oh, linear absolute value, or they think any absolute value makes a V-shaped graph. Linear absolute value does. no other equations do, though, that I can think of. If you do the absolute value of x minus, what is the same problem? X minus 3 squared plus 1, or cubed plus 1, right? Those don't make V-shaped graphs. So be very careful that teaching your students, or students in general, thinking always absolute value makes a V. No, if you have a linear function and you apply absolute value to a part of it, that will make a V, because absolute value causes the negative part of your graph to flip up. But that's the only time. So let's go ahead and take a quick peek. I have three equations here: f of x, g of x, and h of x. Your goal is just to compare the outputs for each of these. Right? We're literally just plugging values in. So take a quick second, plug everything in, see what you get. Don't forget you can use the slope to make things go faster, and then we'll check back in once you're done. Ready, set, go. Alright, well, let's do g of x and h of x first. I think that'll be easier. If we substitute in 1, 1 minus 3 is negative 2, negative 2 plus 1 is negative 1. I know the slope is up 1 over 1, so this will be 0, 1, 2, and 3. Double checking. 5 minus 3 is 2, plus 1 is 3. H of x, same idea. Plug in 1, 1 minus 3 is negative 2, but another negative applied makes it positive 2, 2 plus 1 is 3. Slope of down 1 over 1, these ones will decrease when the x's increase, and we end up here. Kind of the, mirror image of what we saw before. What about absolute value? 1 minus 3 is negative 2, but that's in the absolute value. Absolute value of negative 2 is positive 2. 2 plus 1 is 3. If we try 2 in here, 2 minus 3 is absolute value of negative 1, which is positive 1. 1 plus 1 is 2. If we substitute in 3, I know the output is 1. It's HK form. Substitute in 4. 4 minus 3 is 1. Absolute value of 1 is still 1. 1 plus 1 is 2. 5 minus 3 is 2. 2 plus 1 is 3. Kind of got smaller, then bigger again. Okay. Extrapolating from our results, so working out from our results, what are all values of x that would cause f of x and g of x to have the same outputs? Well, let's compare their outputs. They're definitely not the same there. They're not the same there. But they are here, and here, and here. And I think anything larger than 5 would work as well. How come? Well, any number you substitute in here, like 6, into each of these, 6 minus 3 is a positive, 6 minus 3 is a positive, they both are positive, and then we add on to there. So I think really, since they start at 3 and go larger, we would say that x is greater than or equal to 3 would cause those two equations to have the same outputs. I mean, they look almost the same. Cool. What about the same thing for f of x and h of x? Well, they have the same outputs at 1, and also at 2, and also at 3, but at nothing above that. So it looks to me like 3 and smaller will work. Just to double check though, let's try 0. Right? If I tried an output of 0 here and substitute it in, we get a negative number, negative 3, but then absolute value turns it to a positive. So 3 plus 1 is 4. If I substitute 0 in here, 0 minus 3 is negative, but then what turns it positive? Not absolute value, but an extra negative flips it back to a positive, and then 3 plus 1 is 4. Yeah, they are the same at 0. So we could say here, x is less than or equal to 3. And that's very confusing because I used different colors, so we're going to kind of put this back together, and we'll do it over here. This was x is greater than or equal to 3 in purple, and this one was x is less than or equal to 3 in red. All right, so knowing that then, I would like you please to take f of x, nope, not purple, come on Mr. Grant, we'll do it in yellow, f of x, which is equal to that piecewise function, that absolute value function, x minus 3 plus 1, and rewrite it as a piecewise function, not using absolute value, using g and h. Well, if we look at this, I think we have two functions we need to incorporate. I'm going to do the red one first with the negative, and then the other one second. So negative x minus 3 plus 1. And then the other one in purple was x minus 3 plus 1. When are they equal? Well, this purple one was equal for any x's greater than or equal to 3. The red one was equal to my absolute value for any x's less than or equal to 3. We do need to be careful though. We can't have two equal signs on the same value in a piecewise function. Then it wouldn't be a function anymore. It would be very confusing. So we take one of them off. It doesn't matter which one. And now I think no matter what number you substitute into this piecewise function, it will give you the same result as the absolute value. Okay? Why is that useful? Well, we don't know much about absolute value. We don't know how to do derivatives of absolute value, antiderivatives, graphing can be tricky, solving can be tricky, and so sometimes it is helpful to be able to rewrite an absolute value equation without absolute value, and that's exactly what we did here. Now, let's make sure we also understand what we're doing here graphically, and then we'll get into the calculus portion of this. So, graphically, I'm going to go ahead and show you, and we'll get rid of the rest of these, the equation for the absolute value of x minus 3, close your absolute value, plus 1. This is in HK form, so it's at 3, 1. There's my vertex, 3, 1. Now, if I look at this V-shaped graph, and instead of picturing it as a V, I think of it as two lines. A line moving upwards to the right, so a line with a positive slope of up 1 over 1, and a second line with a negative slope of down 1 over 1, it might make sense that instead of doing one equation that makes a V, couldn't we graph two equations where one equation has a positive slope and one has a negative? And it's actually very easy to take absolute value and change it to two equations because we just want to make sure all the equations share the same point, 3, 1. And how easy is it to graph a line that goes through 3, 1? Hopefully super easy because we know HK form. We do x minus 3 plus 1 and then match the slope. But the slope is outside the absolute value. It's the value out here, so the slope is easy. Up 1 over 1 to the right, down 1 over 1 to the left. So let's look at the first one, the one with positive slope. And you'll notice that it matches our piecewise function. But it goes too far. It stops matching our absolute value graph after the x value of the vertex, after the value that's inside the absolute value. So I want to stop this green equation once we hit, looks like 3. And on Desmos, we do that just by saying x's should only be greater than or equal to 3. And look, now we have a piece of a line that perfectly matches absolute value. But wait, there's more. Here's the other one, doing this one in purple. It has a negative slope, but once again goes too far. We need to cut this off at 3 at the vertex again, right? So this one only we want x is less than or equal to 3. And now we have two linear functions that put together makes the linear absolute value function. Long story short though, it's very easy to rewrite this even without a graph. Just write the same equation twice, but change the slope. One positive, one negative. How are we going to put this into use? Well, if we're dealing with an absolute value function that has to meet an initial condition, you're going to have two choices here. Choice number one is you can drop the absolute value symbol and continue on, right? So that would be equivalent to saying, instead of absolute value, I'm just going to look at this linear function without absolute value. We're going to just call it, parentheses, didn't change anything. But option two is you might have to put a negative out front. Because to get rid of absolute value is a tricky process, so if you can rewrite an equation without the absolute value, you should be golden. You'll know when to put a negative versus not because of your initial condition, right? An answer must always be positive when you finish evaluating the absolute value. So what we're going to try and do here is we're going to rewrite each absolute value equation below so that it's a linear function that contains the initial condition. It's not going to make the exact same V-shaped graph. We're only going to pick one side of it, right? So this f of x would normally be a full V. We're going to see if we can determine which side of this V-shaped graph to keep that contains the initial condition. And we're going to do it without graphing. And it's quite easy to do. So here we go. Part A. We are going to rewrite this equation as f of x equals, I'm going to throw parentheses around this instead of absolute value, and say, ta-da, I'm done. Well, am I done? It's very easy to check. We're going to make sure that this initial condition works in the original equation. And it's just through some mental math. I'm just going to substitute in the 5 and see what happens when I do the math. 5 minus 3 is 2. 2 minus 4 is negative 2. Great, we got the answer we wanted. That means that this is the correct branch of this absolute value. Okay, well, if we want to try another, oh look, the same equation again. How exciting. So we'll do the same process. We'll drop the absolute value and turn it into parentheses and say, let's make sure that this initial condition works. So I'm going to try substituting in 2. 2 minus 3 minus 4. 2 minus 3 is negative 1. Negative 1 minus 4 is negative 5. Ugh, that didn't match negative 3. Now there's two reasons why. Reason one is that it might not have worked in the original equation, so we should probably check that. 2 minus 3 is negative 1. The absolute value of negative 1 is 1. 1 minus 4 is negative 3. So this initial condition is on the full absolute value graph. So what does that mean? Well, it means I picked the wrong branch of absolute value for my linear function. What's the other branch? It's so easy, guys. It's just the negative version. And if I put a negative out here, does that change it? Well, we have an extra negative. Negative 1 with an extra negative becomes positive 1, and that turns to negative 3. Yeah, so my correct branch, or my correct piece of that V-shaped graph is the one with the negative slope. So it's a really easy guess and check. You drop the absolute value, and then see if the initial condition works. If it does, great. If it doesn't, put a negative, and that's it. So there are 2 more for you down here. Try those 2. We'll come back together. Ready, set, go. All right. Well, hopefully you had some success here for this first one. Same idea. I'm going to change the absolute value to parentheses. Oops, this was 1 minus x, sorry, plus 1. 3, 1 minus 3. I'm just checking to make sure I didn't make a mistake, because negative 2, that's 2. 2 times 2 is 4. 4 plus 1 is 5. Now, I'm plugging in 3 right here. 1 minus 3 is negative 2. So I had to use the absolute value to turn negative 2 to positive 2. My guess is I'll need to choose the negative branch. This negative is going to be needed to turn the interior here to a positive. So I'm going to guess that at the first. If you didn't guess that, try it. It doesn't work, try it again. So I'm going to try negative 2 times 1 minus my input of 3 plus 1. Negative 2 times negative 2 plus 1. I need this answer always to be positive, which is why I have the extra negative there. 4 plus 1 is 5. So the branch, or the part of absolute value that contains this initial condition, is this linear function. One more. Oof, natural log. Life's getting crazy. We got this though. So first thing I'm going to do is let's try 3 in here. 2 minus 3 is negative 1. But we normally can't do the natural log of negative numbers, which is why there's absolute value. We need the absolute value to turn that to a positive, and then life is good. So my guess is when we turn this into a linear function, or I guess not linear here because there's natural log, parentheses 2 minus y plus 3, I bet I'll need an extra negative. Where does the negative go? Not outside the natural log. We are just focused on this 2 minus y. And so the negative actually needs to go right here. If it makes you feel better with extra parentheses, it's really the natural log of all of that. Let's try it out. Is the natural log of negative 2 minus, we're using 3, right? 2 minus 3 plus 3 equal to the correct output. This is the natural log of 2 minus 3 is negative 1, but an extra negative turns it to positive 1. Any log of 1 is 0. Yes, we have it. All right, so hopefully I haven't confused you too much, or at least it's making a little more sense now. The idea that if there is absolute value and you need to drop it for some reason, we'll see the reason why shortly, it's very easy. You just drop it, or you drop it and put a negative. And that all has to do with the different branches, but it's a pretty easy process. So let's bring this into play. Here is a beautiful differential equation. We are again going to skip B, because you should be able to do it. You can go back later on, and we're just going to focus on C and D. So, part C. Find the particular solution. All right, separable differential equation. We're going to go with 3 friendly columns again. dy dx, 3 minus y cosine of x. So dy dx equals 3 minus y times the cosine of x. All right, same thing we've done before. Let's divide both sides. 1 divided by 3 minus y times dy equals cosine of x times dx. Guys, this one's a little trickier on the antiderivative. Sorry, it's not bad, but it's a little trickier. So I'm actually going to throw the antiderivative symbol in front of each of these. Antiderivative of cosine, sine of x plus c. Not bad. Derivative of sine, cosine. This one is trickier, though. And I'm going to say, let's pretend that there was no 3 minus first. What's the antiderivative of 1 over y? And hopefully you said, ooh, the natural log. You're right, it is the natural log of y. And so if it's 1 over 3 minus y, it is the natural log of 3 minus y. But there are 2 mistakes with what I just wrote. The first is if you take the derivative of this, and I'm going to erase this, but it's good to see, the derivative of this is 1 over 3 minus y times the derivative of the inside. The derivative of 3 is 0, but the derivative of negative y with respect to y is negative 1. So there would be an extra negative up here. I don't see an extra negative up here, which means to me we need something out front to cancel out that negative. So 3 minus y, and there's an extra negative, or a negative 1 if you want, that's out front. The second thing that's incorrect here is we've learned in the past when you do the antiderivative and end up with natural log, to account for the same domain here where you can substitute in any number except for 3, but because logs you can't use negatives, we must put in absolute value. Must. So definitely a tricky antiderivative. We'll practice a few of these, but now that we're here, let's go ahead and start working through those initial conditions. 0, 1. 0, 1. All right. Negative 1 times the natural log, absolute value of 3 minus, it'll be 1. I'll just need to change colors, equals sine of 0 plus c. So here's my 1, and here's 0. Great. As we clean this up, negative 1 times the natural log of the absolute value of 2. Any sine of 0 is 0 plus c. Cleaning this up further, the absolute value of 2 is just positive 2, so I believe c is just negative 1 natural log of 2. Or you'd probably just see it written negative natural log of 2. Okay, let's move on to the last part. Negative 1 times the natural log absolute value of 3 minus y equals sine of x plus, minus the natural log of 2. You can put parentheses if it makes you happier. I'll probably do that. All right, let's go ahead and isolate y. Divide by negative 1 first, or multiply, whatever floats your boat. Negative sine of x plus the natural log of 2. Looking pretty good. Undo natural log. Yeah, we can do that, right? This is going to be the absolute value of 3 minus y equals e to the negative sine of x plus natural log of 2. Keep it all together. But then wait, we have absolute value here. How do we drop absolute value? Well, didn't we just learn a technique on the previous page that said we're allowed to just drop the absolute value? Kind of, with a caveat. So let's just drop the absolute value. Let's see if 3 minus y is the right branch of our absolute value. How do we know if it's the right branch or not? Test the initial condition. Now, it gets a little tricky to test the initial condition here. You can, right? There's nothing wrong with it. If you substitute 0 in for here, that goes to 0. You're left with e to the natural log of 2. Those cancel and gives you 2. If you substitute 1 in over here, and apologies for the bells, I'm recording at school. If you substitute the 1 in over here, 3 minus 1 is also 2. So I think the left side and the right side are equal here. However, if you didn't want to do that, and you wanted to do this earlier, and I normally do this earlier, I would have done it right from the beginning, right? I would have looked at this and said, oh, let's just try dropping the absolute value at the beginning and see if we need it. And how do we see if we need it? Well, we just substitute in 1 3 minus 1 is 2, right? 3 minus 1 is 2. Substitute 0 in over here, and you also get that negative natural log of 2. Also, because I'm getting a positive answer when we substitute in 1, then I probably won't need the absolute value, because absolute value's purpose is to turn everything positive. But if 1 keeps it positive, we should just be able to drop this all the way through. Okay, or maybe I could have just done it like that. There we go. Once we're here, isolating y is much less scary, right? We did e to the power of both sides. That's where the step below came. These undo each other. And then we just have to solve for y. My favorite technique for solving for y is adding y to the right side and subtracting this monstrosity to the left, like so. And we're done. Okay. Now, you might say, well, wait. What if I just dropped the absolute value? Well, in this case, you'd receive full points. As long as you got the absolute value in the antiderivative, that's a must, 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 and then you dropped it and did the rest, you would get full points here because you didn't need the absolute value based on that initial condition. But if they gave us something else, a different initial condition, right, our antiderivative is still the same. The antiderivative is still negative 1 natural log absolute value of 3 minus whatever y is, equals sine of whatever x is plus c. But let's try this new initial condition here. My new initial condition, the y is 5 and the x is 0. As we go through, and I'm going to work to the right again, as we go through, I'm going to get negative 1 natural log absolute value of negative 2 equals sine of 0 is 0, 0 plus c is c. And so you need to ask yourself, is the absolute value necessary here? And the answer is yes. If you didn't have this absolute value, this would be a does not exist case. There wouldn't be a branch of the equation here. But with the absolute value, it causes that absolute value of negative 2 to turn into a positive 2. And now we found our value of c. In fact, our value of c is the same as it was before. So then, when I go back down to my solving this equation, so negative 1 natural log absolute value 3 minus y equals sine of x plus c, and I think to myself, do I really need this absolute value? Well, we need to get rid of it eventually, otherwise you won't be able to isolate y. So we think, well, can we just turn it into parentheses? If you substitute 5 in here, what happens? Well, 3 minus 5 is negative 2, and we couldn't do a natural log. And so this whole equation would break, and I apologize, my c value should be that negative ln of 2. And so this would break, but the equation doesn't break. The initial condition worked. So 3 minus 5 is negative 2. We don't want that to be negative 2. The absolute value up here turned it to positive. How can we turn it to positive? Put an extra negative out front. I should do that in red. There we go. Now when you substitute in 5, 3 minus 5 is negative 2. The extra negative turns it back to a positive. Okay. How does that change how we solve? Well, barely at all. Okay. So we divide by the negative, and I'm going to do e to the power of both sides. So that gives me negative 3 minus y equals e to the negative sine of x plus the natural log of 2, just like before. How do we solve here? Well, there's two ways. I would probably just distribute the negative into both of these. That'll keep my y positive, right? So it gives me negative 3 plus y equals e to the negative sine of x plus the natural log of 2. And then I just add 3 to both sides. 3 plus e to the negative sine of x plus the natural log of 2. Pretty similar to the other one? Yeah. One's 3 minus, one's 3 plus. But if you had dropped your absolute value here, you would have gotten the wrong answer based on this initial condition. Do you want a graph to help you out a bit? I have a couple graphs here, right? This is actually the slope field of the problem that we just worked through. It's kind of a crazy slope field. There are a lot of different equations going on, right? You might be tempted to say, well, does one equation kind of look like this, and I should do this in red? Does another one, kind of look like this. It kind of looks like that. What's the deal with this line here at 3? Oh, look at this initial condition, or look at this differential equation. When y is 3, what happens? Oh, the slope becomes 0. So it shouldn't surprise you too much that there's a solution at y equals 3. There's going to be a line that runs through the middle. So if they said the initial condition was the point 0, 3, then that would result in a solution of y equals 3. But are there others? Well, of course, we just worked through 2 of them. So let's look at one of our initial conditions, right? The initial condition of 0, 1, the one that we first saw, causes this weird little lumpy graph down here, right? I actually did not see that coming the first time. I assumed it kind of looked like this, but no, it just kind of bounces back and forth like so. All right, well, how would you make the graph be up above? You'd pick another initial condition, like maybe 0, 5. And so this would match the equation that we found at the very end, right? Depending on where your initial condition is, will change the outcome of your differential equation. All right, I have one more to do with you. There is one more page, but this one you can practice on your own. This is just kind of a final concluding fact, and I didn't used to include this because I like the way that I solve my differential equations. I mean, you're partial to your own method, but this showed up on a multiple choice question a couple years ago, and so I thought it was worth addressing. There is a second method for solving differential equations, and I wanted to show that to you right now. I don't like it because I think it's a little bit, I don't know, they do too much with the constant. But let's see if we can follow through. So, first step, we of course separated the variables, right? Separated variables. Okay, next step is we, introduced the integral symbol. Next step, we took the antiderivative. And cool. We're looking good so far. Now what? Well, from here, there are a few things you can do. Some people prefer to isolate y before they solve for the constant. And that's okay, you can. I always like to do the constant first, but what we're going to do here is solve for y first. So to isolate y, the first thing we're going to do is divide both sides by -1. Divide by -1, right? And you can annotate this as you need. Sine of x divided by a negative is negative sine of x. But what is a constant divided by a negative? Well, it's another constant. Some people will say, could I put minus c here instead of plus a new constant? Sure, there's nothing wrong with that. However, what we're really going to do is use kind of this plus c as a punching bag, and it's going to absorb everything we throw at it and grow to a more and more complicated c. So when we divide c by -1, now it's a new c, so I called it c1. The next step is to undo the natural log, so we do e to the power of both sides. We exponentiate each side, exponentiate. And so we do e to the power, those undo, great. E to the power of this side is just e to here. All right, now, they're realizing we have e to this power plus c1. Let's use one of our properties of exponents. Properties of exponents, which says, right, if you have x cubed times x to the 4th, x, there's 7 of those, you add the exponents together. Which means if I had x to the 7th, I could split it into x to the 5th times x squared, or x to the 6th times x to the 1st, whatever sounds good to me. So we're seeing this addition right here and saying, oh, let's separate this, right? Where we take the common base and we do it to each power, because you could put this back together by adding those two and it gives you a new exponent. Now, why on earth would they want to do that? Well, they'd want to do that because e to a constant is another constant. And so you could have even called this right here, that was the worst brace ever, you could have called this right here like C2. Okay, so we're like, cool, that's another constant. It's the third one we've seen so far, but wait, it gets better. Because another way that we can undo absolute value is we can say, hey, we know that there are two different slopes that are going to occur here. Or you could think about it and say the inside of this has to give, or can be positive or can be negative. So it can be equal. Think of this as just pulling out the inside. The inside can be equal to the positive or negative version of the other side. But guess what? Positive or negative, what is all of this? This is just a constant. And then, continuing through, we did the old trick of add y to the right, subtract this to the left. Now we're here. So all of this went through to isolate y. And they isolated y with a constant all the way through. And the reason they do that is sometimes the constant is a gross number and people don't want to have to deal with a gross constant as they solve. But what do we have to do once we've isolated y? Well, then we have to use our initial condition. The initial condition was 0, 1. They substituted in and they found their constant here was 2. Now, we didn't find our constant was 2. We found our constant both times was negative 1 times the natural log of 2. Does it matter? Well, I don't know. Do we even get the same answer? Right? They got y equals 3 minus 2e to the negative sine of x versus ours from part C, we found 3 minus e to the negative sine of x plus the natural log of 2. Are those the same? Well, actually, I think, yeah, they are the same. We clearly see the 3 minus. We can do that same splitty-splitterson thing, right? Where we say it's e to the negative sine of x times e to the natural log of 2. And then e to the negative sine of x. E and natural log undo each other and drops the 2. And now we can see that it's 3 minus 2e to the negative sine of x. Same answer, just done in two different ways. The reason is because of when we solved for the constant. But the really big thing I want to draw your attention to here is that it is possible to undo absolute value by putting plus minus on the other side. And if there is a constant multiplying by everything, then the plus minus gets, we'll say, absorbed into this super constant, and you don't have to worry about choosing which branch is right. I don't think it's hard to choose the branch, and I like to do it early on, but some people prefer this method, and they're like, great, there's a constant, and I can do it this way, and I'm fine. So, just wanted to show you that as an option. I know this video is already quite long, so I apologize for that. But there was a multiple choice one year where they went through and they showed lots of work and said, was there a mistake? And I didn't want you to be confused of like, why are there so many constants? What's happening as we go through? They're just essentially making a super constant. So again, I'm partial to my way of solving this way and choosing the correct branch, but it is ultimately up to you. So I'm leaving you with one more practice problem at the end. It's another natural log one. They're going to be two different initial conditions. You'll have to choose the right branch, and that is it for today and for topic 6. So the rest of the next week or so is going to be spent reviewing. We'll get our test in right before spring break, and then we are on to bigger and better things. Thank you as always for your time, and I'm excited to have you back when we jump into topic 7. It's very short. It's maybe 5 lessons on volume.